It's always good to review what we've already learned. That helps us retain information better. But I also want you to have a good understanding of how motion graphs relate to their equations and relate to displacement, velocity, and acceleration generally. In this video, we'll see how acceleration fits in our understanding of position versus time graphs. The fundamentals of kinematics in physics goes back to the simple linear equation y equals mx plus b. The slope is the difference in y divided by the difference in x, and we refer to the slope as the rate of change of the function. Now, also part of y equals mx plus b is the y-intercept, which I have not marked here on this graph, but that generally is called the initial um, value for whatever your function is. For position versus time graph, the slope has physical meaning. Position is now on the y-axis and time is on the x-axis. In this example, displacement is steadily increasing. The slope is the change in position divided by the change in time. That's our average velocity formula. Again, this makes sense in terms of units. On the y-axis, we have meters, and on the x-axis, we have seconds. So that gives us units of meters over seconds. For motion that doesn't produce a straight line on our position versus time graph, so motion with a non-constant velocity, the basic concept still applies. In this graph, the object is first moving backwards, then forwards, then backwards again, then forwards. The rate of change will be the difference in position over the difference in time. But this time, we're referring to the tangent line to any given point. In calculus, we would say that the velocity is the derivative of the position function at any given time. This is our instantaneous velocity. It's akin to what the speedometer shows you in the car, although we can only measure velocity indirectly. Remember those fundamental units. Note the tangent line I drew on this graph has a positive slope, and it corresponds to an interval of time where the object is moving forward, or rather, or more precisely, the object is moving in the positive x direction. On our velocity versus time graph, so notice this is velocity, not position anymore, slope works the same way. In this example, velocity is steadily increasing. We calculate the slope using rise over run, so change in y over change in x. In this case, our vertical axis has velocity and x is still the time. The slope is the change in velocity divided by the change in time. Well, that's the average acceleration formula. Again, it makes sense in terms of units. On the y-axis, we have meters per second. On the x-axis, we have seconds, and we get something in meters per second squared. For motion that does not produce a straight line on a velocity versus time graph, motion with a non-constant acceleration, the basic concept still applies, just like with the position versus time graph. The rate of change is going to be the difference in velocity over the difference in time. But this time we are referring to a tangent line at any given point. And in calculus, we would say that the acceleration is the derivative of the velocity function at any given point. That's our instantaneous acceleration. Now, I created this video specifically to highlight the parallel between position graphs and velocity with velocity graphs and acceleration. In the next slide, we'll see an example of an actual position, velocity, and acceleration graph that all refer to the same object in motion.